Hi, in this video, we introduce a new approach for computing safety and liveness guarantees through reach-avoid reinforcement learning. Autonomous robotic systems are gradually exiting the confines of factories and labs and becoming ubiquitous in everyday life. In order for their widespread adoption to take place, however, there is the need to trust that these systems will not fail during deployment. In other words, we require these systems to be safe. This being said, safety alone is not sufficient. Autonomous systems also need to be able to provide guarantees of performance, namely that they will eventually perform the task that they are designed for. More concretely, we want to ensure that these systems are live. Crucially, when the problems of safety and liveness are considered separately, there can be instances where safe behaviors lead the system into configurations where task completion becomes unachievable. Both problems, therefore, need to be jointly considered. Recent work in the field of reachability theory has demonstrated the applicability of reinforcement learning tools for solving robotic safety problems. In safety-only problems, we aim to maintain the system within a set of admissible states for which we can guarantee that no constraint violations will occur at all future times. In this work, we look at reach-avoid problems, a broader class of problems for which the system must remain safe while guaranteeing that goal states can and will eventually be reached. Let us introduce a two example which illustrates a reach-avoid problem. Suppose we have a two-dimensional point particle for which we can control its lateral speed, but it has a fixed upper velocity. The goal is to reach the target region at the top while avoiding the restricted areas. A typical reinforcement learning approach might attempt to produce the desired behavior by assigning negative rewards to restricted zones and positive rewards to the goal states. In practice, however, the design of the reward may not always yield the intended result. For example, if the restricted area is thin or the discount factor is high, the agent might violate safety and head straight for the goal. So is there a more suitable formulation? Rather than a sum of heuristic rewards, we can use a payoff that directly encodes whether or not a trajectory achieves the reach-avoid specification by considering both the assigned distance to the target and the closest proximity to restricted region so far. We can ensure that achieved payoff will be negative if and only if the trajectory reaches the target without previously violating the constraints. The corresponding reach-avoid Bellman equation propagates this payoff backwards in time along an optimal trajectory, with early violations overriding later successes. To enable reach-avoid reinforcement learning, we introduce at each time step a small probability of transitioning to an absorbing terminal state for which no more progress can be made. The resulting time-discounted reach-avoid Bellman equation has the effect of slightly pulling better future values toward current success metric.
In fact, our contractive mapping ensures that the fixed point of the discounted reach-avoid Bellman equation is always lower bounded by the solution of the original reach-avoid Bellman equation. Importantly, as the discount factor approaches to 1, we recover the original solution with arbitrary precision. This property guarantees that the resulting zero sub-level set is a conservative under-approximation of the reach-avoid set, and in fact, it becomes arbitrarily tight as time discounting is phased out. We prove this allows us to apply deep reinforcement learning, such as double DQ network, to reason about the safety and liveness of high-dimensional systems. Here, we are showing you the learned reach-avoid value function, as well as two example rollouts for Rubies car dynamic system. And this is the analytic reach-avoid binary outcome. As you can see, we have approximation errors near the reach-avoid set boundary. We know the approximation errors are inevitable for deep learning-based methods, especially in high-dimensional systems. Therefore, we propose a shielding scheme. Here, the robot wants to reach the goal while maintaining in the gray reach-avoid set. Assume we have an accurate simulator. Once we attempt a candidate action, we simulate forward a short trajectory with this action followed by the reach-avoid policy. And we check if the reach-avoid policy can maintain the safety and liveness of the system. If not, we reject this candidate action and instead we execute the reach-avoid policy. If we can maintain the safety and liveness, we execute the candidate action. The shielding scheme guarantees a recursive feasibility. This reach-avoid set can be obtained by the policy rollout. There is no false success. Thereby, it ensures the success of shielding scheme provided we have an accurate simulator available at runtime.
We also test the double Q-learning reach-avoid algorithm on a modified OpenAI Jaime lunar lander environment. As expected, value function slices with initial lateral speeds cause the reach-avoid set to protrude near obstacles and the edges. In this animation, we show how from an initial unstable configuration, the lander is able to correct course by avoiding the right edge and heading straight for the target set. In this video, we have presented a discounted Hamilton-Jacobi reach-avoid reinforcement learning formulation, which we hope will be used for computation of safe and live controllers in safety-critical settings, especially in high dimensions, as well as a solid foundation for safe reinforcement learning through shielding. Thank you very much.